Hello, good evening, and welcome you all for today's lecture. Actually, everybody can unmute yourself today. If there is a disturbance, we have to mute you all. But anyway, we make sure that everybody is muted while the lecture is going on. Thank you. And as usual, I am here today. I am also Kamala Gunwadana, fellow representative of this council, and sharing this knowledge sharing subcommittee of Civil Engineering Sectional Committee. Our today's webinar is again a continuation of medium-rise buildings and constructions by our Professor Jayasinghe, and this is the 7th lecture for the whole series. You all are now very familiar about the activities of Civil Engineering Sectional Committee, and your participation was really remarkable in the previous lectures and other webinars also. So that itself an appreciation of our work, and we appreciate your return as well, right? So everybody, we are starting the today's event right now, and it is an honor for me to make this instigating note, even though you all are known this speaker today. He's always with a bag of full stuff in his area, and that is how he has taken this challenge of giving you this best knowledge about the title. So I will call over again Professor Jayasinghe, Senior Professor of Civil Engineering at the University of Moratuwa. His topic today is structural forms for tall buildings. He will explain you how the lateral forces can dominate the selection of appropriate lateral load resistance system together with various structural forms and systems that can be successfully adopted for tall buildings of different heights. I wish to remind you to join tomorrow. We have a webinar before I invite Professor again. How environmental and social destruction caused by Umaoya multipurpose development project was averted is a question. It's organized by the Water Forum jointly with our Civil Engineering Sectional Committee. Tomorrow's present is Engineer Dr. Jagat Gunatilaka. And we have day after tomorrow, design of box structures on expressways and highways by Engineer Asel Sumanisinghe. Now you all know who is the presenter for day after tomorrow also. So without a further ado, I call Professor Jayasinghe to take over.
Thank you, Engineer Kamala. Thank you, Engineer Kamala. In addition to that, there's another lecture tomorrow at I think 5:15. There's one lecture on agricultural sectional committee, and I am the speaker. I'm going to speak on modern organic farming that based on all the work that I have done on organic farming sector. I have actually spent a lot of my money to promote organic farming, and we have a lot of experience gained with so many things. So we thought of actually sharing all the knowledge that we have gathered. So tomorrow there's another lecture on organic farming as well. We call it modern organic farming, which is very different to the kind of organic farming that is advocated by the agriculture department and Ministry of Agriculture. They are all talking about organic farming, but if you participate in tomorrow's lecture, you'll find what we call modern organic farming is very different to what is actually advocated by the Ministry of Agriculture. So today, we are going to talk about structural forms for tall buildings. And you all know tall buildings can be constructed to meet various needs like office space, residential space, commercial space, and sometimes you get very tall buildings where you are going to combine so many different things. And so basically you have to resist gravitational loads, the vertical loads, and lateral loads. And some of these loads are permanent nature, like the self-weight, whereas others are variable. So in Eurocodes, we get permanent loads and variable loads. And so basically, you have to ensure that there's adequate ultimate limit state, so that ultimate limit state strength, so that, overall you will have a factor of safety of at least 2. And most of the concrete structures will have a factor of safety of 2.5, in the range of 2.5. But one of the very important things you have to keep in mind is, when you are dealing with tall buildings, any structure like transfer plates, which can be categorized as key elements. Key element is one where the failure can cause a significant collapse of the building. You must not go for this kind of very low factor of safety like 2.5. You must go for much higher factor of safety like 4 or 4.5. The reason is, the moment the factor of safety is higher, the crack widths will be very small. The moment the crack widths are very small, what you find is the durability of reinforcement will be much higher. So it's very important that you keep in mind what the philosophy called risk-based design. That means, you assume that different elements can have different risks when it comes to failure. For example, if you take a beam, the beam does not fail at the support, but it can easily fail in the span. So you need to have a higher factor of safety in the span than the support, because support, the maximum that can happen is there will be a plastic hinge forming at the support, and that plastic hinge will allow some rotation in the beam. With that rotation, the more moment will be transferred to the span. So if a failure occurs, it will be in the span, not in the support. So that's why we allow moment redistribution when you are designing, knowing very well a beam will never ever fail at a support, but it will always fail in the span. So when you are designing a beam, if it is an important one, in my case, I would have little bit of additional reinforcement. So similarly, you would have heard about this the collapse of a building in Miami, in America, in Florida, and in that building, it looks like they have not considered the construction sequence effect when they were designing the building, and because of that, they have under-designed the transfer plate by a small margin. But this kind of small margins can cause slightly higher crack widths, and with a slightly higher crack width, you will find the whole structure is okay except the transfer plate, because transfer plate has undergone a higher degree of deterioration than the rest of the building. So when you are inspecting, you inspect the whole building, it's all fine, then you might not suspect anything wrong with the transfer plate because the deflections are so small, very difficult to see the reflections. Then one day, transfer plate fails because its capacity is exceeded. The reason is, initially it has been under-designed, and then you find crack widths are more. Then gradually the factor of safety will reduce with time as the reinforcement deteriorates. And one day, the factor of safety can become less than 1. That day, a disaster can happen. So you have to always keep in mind, when you are dealing with large structures, never ever design based on codes. You must have your own rules. And one of the rules is, always look at the member you are designing and see where it can fail, the location it can fail. Ensure you have some extra factor of safety. And at the locations it can never fail, just have the marginal design so that you have the normal factor of safety. And don't over design locations that can never ever fail, but always think of having little extra capacity at the places where the structure can fail. So always keep this in mind. The moment you keep this in mind, your designs will become very safe designs while they are economical, because you are removing all the steel from places where failure cannot occur, and you are adding some steel at places where failure cannot. For example, if I am designing a two-way slab, I will minimize the reinforcement everywhere except one place, and that place is the short span direction in the span. In the span, I will consider long span as not critical. So I will use the minimum reinforcement I can have, but in a short direction, it can fail. So because of that shorter span direction, I will be little generous. Everywhere else, I will try and minimize as much as possible. And you know, these days, there's a huge supply chain management issue caused by COVID related restrictions, and many parts of the world supply chains have collapsed, and it might take 5-6 months before the supply chains become come to the normal level. Until such time, many parts of the world will have huge shortage of materials. It's had nothing to do with the dollar shortage in Sri Lanka, because it's a worldwide supply chain issue. And because of that reason, you'll find that many goods will be very expensive short term. But the chances are the prices will come down as the supply chain issues are sorted out. And today, if you are doing a design, you have to always keep in mind, steel is very expensive, and per ton cost can vary between 250,000, 350,000 to 370,000, or it can go even higher, depending on whether you can buy steel freely or whether you have to buy it in black market. So these are all happening, and it's the same with cement. And yesterday it was told 35 cement importing companies have withdrawn. So that is the reason for huge shortage of cement. So likewise, everywhere you find shortages, and these shortages will make some of these construction materials very expensive short term. So we have to always look for alternative systems. And that's why, I am doing another lecture on the first Wednesday of March. I am planning to do a design on carbon zero buildings, and in that I'm going to make a presentation on carbon zero buildings, and in that one I'm going to show you how to construct without using concrete or with minimum use of concrete, but still constructing multi-story structures like 3 to 4 story structures with minimum use of concrete but with some use of cement. And I'm going to show you how to make structures almost carbon zero when it comes to the carbon footprint, because these structures would be much more thermally comfortable than normal structures, and the embodied energy would be at a very low level. So because of that reason, you'll find these structures are very very environmentally friendly structures, or green structures, or sustainable the buildings with sustainable principles. So there are so many different things that are around us, and this is a challenging time. So even when you are designing a tall building, you have to be mindful about it. We should not think we are going to have enormous amount of material, unlimited supply of material. We must try and make them as optimum as possible. So when it comes to optimum structures, again, we have to think of normal reinforced concrete structures, where say 50 to 60% of concrete is not doing anything. For example, in a slab, we have hogging moments and sagging moments in every section. Whatever the moment, below the neutral axis, the slab is cracked. So when you have a 150 millimeter thick slab in a structure, only 20 millimeters or 30 millimeters will be above the neutral axis. The remaining 120 millimeters will be below the neutral axis. So this concrete of 120 millimeter thickness is just adding weight, except providing cover to reinforcement. Then there are two penalties here. One penalty is you are using this reinforcement for two reasons. One is to carry flexure. What is the other reason? Other reason is to prevent the shrinkage and thermal cracks in concrete. So if you can have a system where you are going to remove all these cracked concrete, that means you are going to remove most of the concrete in the tension zone, then you can have a very economical structure. And so I'm going to talk about all these different things under slabs. We'll have a very detailed lecture on slabs in buildings, slabs in tall buildings. Because the reason is, in a tall building, we have one element that will be repeated 50 times in a 50-story building. What is that element? That is the slab. We are going to repeat the slab. We design one slab. We are going to repeat it 50 times in the same. So if you can make a 10 millimeter reduction in the thickness, when you repeat it 50 times, you are going to make a reduction of 500 millimeters of concrete, or the concrete that is sufficient for 3 more floors. So it's even the minute savings are so important. So that's why we say in tall buildings, don't change in 25 millimeter intervals, change in 10 millimeter intervals. So the slab can be 140 millimeter, 150 millimeter, 160 millimeter, 170 millimeter, 180 millimeter, 190 millimeter, or 200. Don't change the slab thickness in 25 millimeter intervals, because in a tall building, even such a change may be too much. The reason is we need very much optimized structures. If you save 1 ton per slab, then you are going to save 50 tons in a 50-story. It may not sound big, but the moment you start saving like this, you might not save 1 ton, you might save several tons per floor, and these several tons will finally add to huge amount of extra expenditure that is unnecessary. Then you'll ask why. The reason is slabs never ever fail in a building. Then you'll ask why. Why slabs do not fail in a building? Slabs do not fail in a building because the buildings are large and slabs of sufficient thickness can develop what we call arching action, because our beams are not going to deform because they are strong beams. So when the slab tries to deflect, it can develop what we call arching action. And because of arching action, the slabs will be little more stronger than what you actually anticipate. And because of that reason, it's very hard for a slab to fail, provided that you have compacted the concrete well, you have cured the concrete well, and also you have used reasonably good quality concrete, and especially concrete containing at least 10 to 15% fly ash. Then you'll ask why. Again, you have to keep in mind, when we have fly ash, the chloride resistance of concrete will be high. When you have fly ash, chloride resistance of concrete will be high. When you have fly ash, the workability of concrete will be high. When you have fly ash, the carbon footprint of concrete will be lower. There is advantages. And then when you have fly ash, most importantly, the concrete is going to gain strength over a longer period of time. It is not going to stop gaining strength in the first 10 days, because when you look at the cement composition these days, cement composition has changed a lot. 50 years ago, when you take cement has 2 main ingredients that can contribute to strength, in addition to the very important ingredient, which is called calcium aluminate, which will give the initial strength, which is only important only for the initial strength. But after that, there are 2 very important ingredients that can give strength. One is called tricalcium silicate, the other one is called dicalcium silicate. Tricalcium silicate gives the strength after 14 days. Sorry, tricalcium silicate gives the strength after 1 day until up to 14 days. And dicalcium silicate gives strength from 14 days onwards. So if you take a cement 50 years old, then you will find those cements had 50% tricalcium silicate and 25% dicalcium silicate. So 50% tricalcium silicate will contribute to early strength from day 1 up to 14 days. And beyond 14 days, the strength gain will be lower, but because there are 25% dicalcium silicate, the concrete will continue to gain strength up to 28 days and even beyond. But today, if you look at cement, most of the cement contains 60 to 65% tricalcium silicate and only 5 to 10% dicalcium silicate. So what is the end result? Today, after 3 days, 4 days, you get enormous strength. After 7 days, you can get 28 days strength. Then after 14 days, the strength gain is very slow, very slow. And you will find that 28 days strength is available in 7 to 10 days. And you must know the reason. The reason is cement companies have done two things. Number one, they are adding more tricalcium silicate. Number two, they are grinding the cement finer so that you will end up with a higher strength, high early strength, but not very high long-term strength. Long-term strength gains, and because of that reason, we like concretes made with fly ash. The moment you have fly ash, the byproduct of the hydration process, calcium hydroxide will start reacting with fly ash, and what is the end result? You are going to get a higher strength concrete, and a concrete that is capable of gaining strength over a longer period of time. Even after 90 days, you will find still the strength is increasing slightly. So which is a better concrete? Concrete containing fly ash is much better because it has lower carbon footprint, it has low embodied energy, it has desirable properties, it is more corrosion resistant, and it is also could be more sulfate resistant, and most importantly, fly ash containing concrete can be made slightly cheaper because fly ash can be obtained almost at a lower cost, much lower cost than 1 kilogram of cement. So in today's prices, 1 kilogram of cement can vary between 30 to 40 rupees, whereas 1 kilogram of fly ash should be available around 10 rupees because fly ash is a byproduct of our Norachole power plant. So good quality fly ash should be available in Sri Lanka for less than 10 rupees a kilo. So now you can see, when you look at all these good properties, you make a good quality concrete using fly ash, good quality cement, and then you use super plasticizers, use less water, you can make dense concrete, flowable dense concrete, and then you'll end up with a good quality concrete in the slab. And if you have ensured 20 to 25 millimeter cover, all the steel in the slabs will be very safe. They will not undergo any deterioration. And with that, you can easily say, even with 20 millimeter cover, you can easily say you have a slab that is not going to fail easily. And if you look at the live load scenario, unless you go for storage, it's very hard to find enough furniture or people who are having sufficient weight to cause the kind of imposed loads that you have assumed in your structural design. So because of that reason, always keep in mind, slabs are very safe. The only critical location in a slab is the short span. So if you want to be generous only there. Other places, think of using not only 10 millimeter steel, even 8 millimeter steel. And if you break a building which is 56 years old, then you will find they have even used 6 millimeter wires. but today it's not allowed, but you can easily use 8 millimeters. But when you use 8 millimeters, you have to have some timber planks on the steel mat, because if you walk on the steel mat, it can deform. So because of that reason, you need to have sufficient timber planks on the slab for walking. Until you complete the concreting, you need to have sufficient timber planks on the steel mat, so that when you're walking, you'll walk on the timber planks, not on the net. But if you have a 10 millimeter net, even if you walk on the net, nothing will happen. But if you are if you are having 8 millimeter wires or 8 millimeter reinforcement in the slabs, then you have to be a little careful during construction. And the other most important thing is always go for proper cover blocks, which come with the binding wire, so that the cover blocks will remain at the correct location during the concreting operation. So these are very minute things, but very often engineers overlook this, and then they say slabs deteriorate, and nobody can understand how slabs can deteriorate, because slabs are one of the safest in the structure. And the moment you know slabs are one of the safest in the structure, you can always think of optimizing the slabs, so the vertical load can be minimized. And the advantage of minimizing the vertical load is very evident when you have end-bearing pipes. But if you have good soil, you have the skin friction in addition to end-bearing, then you will find, even if the dead weight of the structure is slightly higher, you are okay. But if you have very weak soils, where you have to rely a lot on end bearing and the skin friction within the bedrock, then you'll find minimizing the weight of the structure is also important. So in a tall building, we have vertical loads, lateral loads. Lateral loads we have no control, but vertical loads we can control. We must try our best to minimize the vertical load by using reasonably high strength material. So if you can minimize the thickness of a slab by using 40 megapascal concrete or 35 megapascal concrete rather than using 25 or 30 megapascal concrete, you should always look for these options and go for try and use them. And to do all these things, your construction quality assurance scheme should be very good at the site. Not only the project management part, but the quality assurance scheme should be very accurate at the site. And you can't afford to have any leaks in the shutters. You can't afford to have a situation where you ignore curing of the slabs. The curing of the slabs will be very important, at least for 7 days, because we are using concrete with cement with a lot of tricalcium silicate. So still curing the slabs for at least 7 days, at least until the shuttering of the upper floor comes, so that the lower floor becomes shaded. You have to do it, because our climatic conditions are not conducive for cement to gain strength. You have to look after the concrete. So why I said all these things is, when I say structural form, it is not only the structural form for lateral resistance, but the vertical load carrying system. Optimization is also very important when it comes to tall buildings. I'm talking about the range of 40, 50, and then you can think of 60 to 70, and beyond 60 to 70, we generally call them super tall buildings. And we are not going to touch a lot about super tall buildings at the moment. And we are planning to get another expert, Dr. Dhammika Maharachi, who has already designed a 120-story tall building, sharing his expertise with you. And at the moment, he is in Sri Lanka. And I'll see whether he is willing to do a lecture And if he's willing to do a lecture, we can even have an extra lecture one of these days, just to hear what hear or share his experience. But definitely he will come on this series and he will do some lectures. So if you look at the situation, the situation is we have to have thorough knowledge about the lateral load resistance system. We need to have thorough knowledge about the vertical load resistance system. And we need to optimize both systems if we want to have an economical structure. And it is very important in today's context because we are having serious problems with supply chain management. So when it comes to lateral deflection of a structure, the lateral deflection should be controlled to height of 500. And sometimes we go for even height of 600, height of 700, but it depends on how much you have optimized. But generally, it's important to control the lateral deflection to height of 500. The relative drift between two consecutive flows also should be controlled very carefully. And height of 500 is a good indicator for that also. The reason is if the deflection between two flows is more than height of 500, then you might find the operation of the lift may be a little difficult because the lift has to go not in a vertical path but in a curved path. So lift, you'll find the wheels of the lift which are on the rails will start making unnecessary noise because lift is not going in a vertical path, it's going in a curved path. So you have to always check inter-story drift. That means the drift between two consecutive flows must be checked in addition to the overall deflection of the building. The reason is in most of the buildings, I showed you earlier in one of the lectures, the shear walls behave in cantilever mode. The frames can behave in the shear mode. So because of that reason, the cantilever mode dominates at the lower part of the building, and the shear mode dominates in the upper part of the building. Because of that reason, the overall deflection can be less than what you get with cantilever mode. So in that, when you look at that, you can see in the middle part of the building, you can get the highest inter-story drift, the drift between two consecutive floors. And you must look for that and ensure that it is less than height of 100. So then I can again look into another matter. When you are talking about steel and concrete, steel was very popular in the earlier buildings. And if you look at Empire State Building has steel, which is as much as twice. If we design the Empire State Building today, Empire State Building was designed in 1920s, late 1920s. It was constructed during the Great Depression in America. And there's another very important structure that was constructed during the Great Depression, and that is called the Hoover Dam. And that actually created such a massive reservoir in America. And the construction of that reservoir dipped the whole the crust, earth crust in that area by 60 millimeters. The weight of the water is so much, the earth crust dipped by 60 millimeters. And in Sri Lanka also, people talk about earthquakes caused by Victoria Reservoir. And Victoria cannot cause earthquakes because the quantity of water that we store in Victoria Dam is so small, it cannot cause much deformation in the earth crust. But whereas this particular huge dam in America has caused a big dip of 60 millimeters. Even then it's 60 millimeters. So you can see Victoria Dam can never ever cause any earthquakes in Sri Lanka. So as Kotmale Dam and Ranveligal Dam. But many people talk so much rubbish in this country, and you will find people are talking about earthquake zones forming south of Sri Lanka. But that is in geological scale. We are talking about millions of years. It will take at least a few millions of years to form some kind of breaking up south of Sri Lanka. It will never ever happen in our lifespan. So always think that things happen in the earth in geological scale. When we talk about our buildings, we are talking about a lifespan of 100 to 500 years. Then you'll ask, why I talk about 500 years? That is because now you can see, if you look at the very early buildings in the world, most of those buildings are still standing in America. And if you look at Empire State Building, 1931, now it's close to 90 years, still it's standing. So you can see, the buildings should be designed for a longer period than 100 years. Although the codes say 100 years is sufficient, now it has come to the level we have to say 100 years is not sufficient. We should start looking at 500 years. And the only way you can look at 500 years is the moment you master the concrete technology and go for higher strength concrete. And higher strength concrete is achieved not by using too much cement, but by using other techniques, like controlling the water cement ratio, controlling and adding fly ash so that the strength can gain over a longer period of time. And that's where the Euro code comes to the scene. Euro code allows us to use higher strength materials, and strength of the cubes can go up to 105 megapascal in Euro. And the corresponding cylinder strength is about 90 megapascal. So, what is the difference between steel and concrete? What is the difference between steel and concrete? Can anybody answer? There's a huge difference between steel and concrete. The steel is very strong. It has an elastic modulus of 200 kilonewtons per millimeter square. Elastic modulus of 200 kilonewtons per millimeter square. Concrete is much weaker, but concrete is out of natural materials like the crushed stone, sand, all that we can find around us, plus some manufactured material again using the natural materials, and that is it. In addition to that, we can have byproducts like fly ash, we can also have silica fume, and we can also control the water cement ratio significantly by adding very advanced admixtures. And we are very fortunate that we have few companies who are manufacturing these chemicals in Sri Lanka. And because of these companies, today we have the ability to go up to 150 megapascal. 150 megapascal. That is beyond what we can achieve, what is allowed in Europe. So you can see, if you are capable, if you are willing to take challenges, then you can go up to 150 megapascal in Sri Lanka, which is again allowed in practice, because if you want to do something beyond the strengths allowed in a code, then you have to link up with a good university and then do some research, come up with rules, new rules, use them cautiously, and then go for stretch the limits. And when you are going for very tall buildings, super tall range, always you have to stretch the limits. Then I ask the question, what is the difference between steel and concrete? Concrete has a very important property. When you control the water cement ratio, go for higher strengths, elastic modulus increases. Because the elastic modulus increases, when you go for higher and higher strength concretes, you get a super strong material. And when you are using high strength concrete, the main advantage is stiffness of the structure increases. The biggest drawback with steel is elastic modulus does not change. Even with high strength steel, elastic modulus is still 200 kilonewtons per millimeter square. Still, elastic modulus never changes, whereas concrete, as you improve the quality of concrete, go for higher strength concretes, the stiffness of the structure increases because elastic modulus increases. That's a very important thing that you have to keep in mind, and now you can see why all the super tall buildings that are designed today, concrete is becoming a very important material, and that is the number one choice. Why? Because the modern codes of practice like ACI code and Euro codes, they all allow us to use high strength concrete and make the maximum use of higher elastic modulus. So don't jump to the idea of using 25 megapascal or 30 megapascal concrete saying, I'm going to design a reinforced concrete. Never do that. Let's think, what can I achieve if I try and go for high strength concrete? And with high strength concrete, I'm going to get a more robust structure, a stiffer structure. That means the lateral load resisting system is going to work better when we use higher strength materials. So you have to keep that also in mind. So on one side, you have to use higher strength materials and optimize the structure. That is the vertical load carrying system coupled with horizontal load carrying, the horizontal members which are actually transferring the vertical loads onto the vertical load carrying system consisting of columns and beams. So steps also can be optimized. Then the moment you optimize these and use high strength concrete in columns and reasonably high strong beams, then you'll find the stiffness of the structure has increased. Because the stiffness has increased so much, now you find the behavior of the structure is better. And what we say a good behavior is the drift is low, the deflections are low, and most importantly, the wind-induced accelerations are also very low. So it's very important to keep in mind, concrete is a super material, ideal for tall buildings, but you can make that advantage to maximum effect is only if you have mastered the guidelines given in the Euro code with respect to the gain in strength, the materials, and you have to become a master of the game when it comes to concrete technology. So I'm going to conduct a lecture on concrete technology also one of these days. And if you want, we can have it. That all depends on your choice. If you want to have a lecture at a later date, we can have it on a later date. But if you think it's important to have a lecture on concrete technology, before we move lot into tall buildings, please put it on the chat box. Based on your requests, we'll see we can have a lecture towards the end of February or early March on concrete technology. So it's all up to you, and just indicate your preferences on the chat box so that we can organize the lectures based on your choice, because now we are opening up little by little, because earlier it was very structured. Now we are opening up and we can accommodate your requests. So we are not touched foundations so far. We will not touch foundations immediately. But we'll first cover the tall buildings, little bit of modeling, little bit of more understanding. And after that, we'll start covering foundations for smaller buildings. And again, we have to start smaller buildings with isolated footings, and then inverted type footings, and then the rough foundations, and finally pile foundations. So there's a series of lectures, and I'm also planning to bring in Dr. Nayindi Zilla to conduct lectures. on foundations, where he will show you how to make use of the sophisticated foundation design techniques based on limit state theory for foundations. And those methods are given in Eurocodes. Eurocode 7 covers the foundations, and it's all given in the Eurocode, I think 5 or 6. So one of these codes is on foundations, geotechnical aspects. Masonry is 6, earthquake is 8, foundations is 7. The foundations is Eurocode 7. So look into, if you look at those, you find it gives so many different methods of dealing with foundation design, and you can still use the old method where we design the foundations based on serviceable limit state. That is also allowed, but it allows more advanced methods, and it has to be taught by a geotechnical engineer, not a structural engineer, because my geotechnical engineering knowledge is not sufficient to teach those methods, because you have to go deep into the friction angle and cohesion when you are dealing with those methods. So ideal person is Dr. Naindi Silva. He agreed. So he'll be taking those lectures. So you can see the moment you go into Eurocodes, there's huge amount of interaction, and which means you must broaden your knowledge a lot. So we'll try and cover those things in greater detail as the time permits. So you can see foundations are very important. We have to optimize not only the piles, but you have to consider the options like rafts and pile rafts. And what is the difference between a raft and a pile raft? In the pile raft, you will get some friction piles and a raft. So when the system is loaded, the piles will carry some load, raft will carry some load, and raft will ensure the soil is loaded everywhere. But the beauty is, even if there are weak pockets, still the raft will not tilt. It will retain its shape, and generally in pile rafts, the maximum deflection in the raft foundation occurs in the center, and you will get a concave type shape with the maximum deformation towards the center of the building. And because of that reason, you will find the soil is stressed at the location where it has the highest confinement, because building is confined in the soil, and if you get the highest deformation in the center, then the soil is stressed highest where it has the highest confinement, which means you are having advantage. That's why they used friction piles in Petronas Tower. The reason is, in Thailand, you cannot find bedrock. Even if you drill 300 meters, you can't find bedrock. So they went up to 125 meters and created a pile raft so that the whole building will settle by some amount, and piles will settle, the raft will settle, and all that will stress the soil, consolidate the soil, and make the soil better. And then you have a combined system carrying all the loads. So it's a very advanced design, and again, you can do modeling of that type of systems, but the most important thing is how to create that type of systems in Sri Lanka. That type of systems, we have developed a method of making use of pile rafts, but for that you need laterite soil available in Sri Lanka. So if you have a location high, not a low-lying land, not a land full of peat, it's a good land. You get laterite soil. The bedrock is 20 meters below, but it's laterite soils. Then you can consider using pile rafts. On the other hand, you take the piles up to the bedrock, and then the question is, Do we need a raft? Answer is no. There's absolutely no need to have a raft, because even if you have a raft, it will not be mobilized. The reason is all the piles are resting on bedrock. The deformation of piles will be limited to 5 millimeters, 6 millimeters. And to mobilize the full capacity of a raft, you need 50 to 60 millimeter settlement or even more, which means you are not going to get the effect of a raft. But in Colombo, you'll find there are many buildings having so many piles and having 3 meter thick raft, cast with enormous amount of trouble, cast by taking enormous amount of trouble to control the temperature, to ensure that delayed ettringite formation will not occur. And last time I told you, you can download the paper on delayed ettringite formation and all the solutions that you need on the concrete technology by typing M.T.R. Jayasinghe DEF, and it was authored by Engineer Nuwan Senaka Wanikaratna and Myron. Myron is now has completed his PhD and working in Australia. And Nuwan Senaka Wanikaratna is the engineer who has designed the tallest building in Sri Lanka, having 77 floors. And his design was sent to OR partners for checking, and they said it's the perfect design. So you can always read this paper, and we all worked, and we should be thankful to Maga Engineering also, because they allowed us to take so many readings in their actual structures. And because of that reason, we were able to calibrate the software that we use for generating, predicting the temperatures. And once we calibrated the software, we use it to generate all the different situations. And then we converted those to a set of charts. Today, you are so lucky. Within less than 5 minutes, you can select a suitable mix depending on the thickness. And you have different and you can have different placing temperatures, and how to do adjustments to all those various factors are all given in that paper. So download the paper and read it, and you can gain a lot. And so how foundations is a critical factor. And if you want to know, we had fractured rock at Altea site. And the structural engineer, I was only the checking engineer. Structural engineer is a very brave person. And he insisted socketing 10 meters into the fractured rock. And he knew very well that it's not going to move. When the geotechnical engineer proposed a capacity of 6,500 kilonewtons for a 1.2 meter diameter pile, the structural engineer said 11,700 kilonewtons. It's close to double. And for 1.5 diameter piles, he proposed 11,700 and something like 17,000 kilometers. 17,000 kilometers. And most of the projects in Sri Lanka before that, we have used only 10,000, 11,000 as the capacity for 1,500 diameter. Ensure that this kind of high capacity is available, we used 60 megapascal concrete in piles, 60 megapascal concrete. Then you'll ask, what is the cost difference between 30 megapascal concrete and 40 megapascal concrete? Per meter cube, the price difference is only about 1,500 rupees. It used to be about 1,000 rupees. Now it will be about 1,500 rupees per meter cube of concrete. So when you're going for 60 megapascal concrete, it may be about 4,000 rupees more expensive than a normal concrete. But if you look at the concrete per cube price today, that is 22,000 kilonewton, 22,000 rupees to 23,000 rupees per meter cube. It used to be about 18,000 rupees. It has gone up by about 4,000 rupees, 5,000 rupees. And when you compare that, even if you have to use 4,000 rupees more per meter cube, but if you are going to get a much higher load carrying capacity, it's worth considering. It's worth considering going for a high strength pipe. Then again, you'll ask, there are so many restrictions on the British code, but most of those are not available in the Euro. So the moment you go for Euro code, again you can see, you can stretch the limit. You can stretch the limits. So what are the structural forms? The structural forms means you will have large in office buildings, you need large free spaces so that you can use lightweight partitions and do all the partitions. In apartment buildings, you need a lot of partitions. So in apartment buildings, one of the options is above the transfer plate, you can have a large number of small concrete walls, thin concrete walls of 225 millimeter thickness or 250 millimeter thickness, and so many walls, which means you need a transfer plate structure, as I explained last time. On the other hand, there's another option. That option is use few large columns and have a large span, then a large slab. But again, to optimize the slab, you can have secondary beams and make the slab thinner, and then go for lightweight partitions. Go for lightweight partitions of density 700 to 800 kilograms per meter cubed, lighter than water, and ensure the partition wall thicknesses are 100 to 150 millimeters. That is another option. So there are so many different options. So we'll not talk too much about those options, because I can explain all those different options in a later day. But today we'll concentrate more on the lateral load carrying system. And when it comes to apartment and all those buildings, you have different set of requirements. And in office buildings, we like to have all the services below the ceiling. That means the floor-to-floor height of an office building will be 3.6 meters, whereas we need very few services in an apartment building. So the soffit of the slab can be converted to the ceiling. So ceiling is a soffit, which means you can easily maintain 3.1 to 3.2 meter floor-to-floor height. So you have to always look for different options. And again, now sometimes the beams are thicker than the walls. So how about a structure where we completely avoid beams? That is the flat slabs. These days we don't do flat slabs with reinforced concrete because they are so uneconomical. We do flat slabs with pre-stressed concrete. And there are so many buildings in Sri Lanka having all floors pre-stressed. And there's one hotel in Kandy, about 18 or 20 floors. All the floors are out of pre-stress, designed by the engineer called Anurad Silva. He's a very experienced engineer, he has designed some 74-story tall building as well. But not in Sri Lanka, but in Dubai. So he's one of the, he's now doing a PhD with me, and we are looking at how to go for the buildings having more than 150 floors. So that is the kind of work we are doing. And then if you look at Colombo city center, all the floors are pre-stressed concrete. And Altea, all the floors are pre-stressed concrete, so that you can avoid beams. And also, the main advantage of pre-stressed concrete is because you are using tendons to carry the loads, the curved parabolic tendons and straight tendons to carry the loads. Whenever you have a concentration of loads, you can always use additional tendons and carry those extra loads to the supports or to the columns. So there are so many advantages of pre-stressed concrete slabs. So that's another option you have to take into account. And Eurocode is again strong in this area, so you can actually make use of the code provisions. But in pre-stressed concrete design, we can do designs a lot. A lot of design work can be done by using fundamentals the moment you have the basic guidelines. So there are so many options or so many areas. Now you can see today only we are talking about tall buildings. So many things can be opened up that may not be very important in low rise and medium rise. One is on concrete technology, other one is on slabs, other one is using systems other than reinforced concrete like PT and precast beam slab systems. And also I showed you why high strength concrete can be so important when it comes to tall buildings, because stiffness can be increased by using high strength concrete. So there are so many different structures that we can use: base frame structures, that is steel structures; rigid frame structures, that is beam column structures, again ideal for concrete; infield frame structures, those are the structures where the masonry is used as an infield material; shear wall structures, the most common structural form. We like shear wall structures a lot because shear walls can stabilize the structures a lot. And then coupled shear wall structures, when that is a very useful system, we can nearly double the length of a shear wall the moment you combine two shear walls aligned. So you can improve the system, the behavior a lot. Coupled shear wall structures, but these are more vulnerable for earthquake damage, so we have to do proper earthquake designs for these coupled shear wall structures. Wall frame structures, that is the interaction between strong walls and strong frames. So you'll make the frame strong, wall strong, then you'll find you get a strong interaction between these two, and the behavior of the building is not a cantilever mode, not the shear mode, but it's a combination of cantilever and shear, where the cantilever mode dominates at the bottom, where the deformation is zero, the rotation is zero, and in the top, the building bends back, and that is due to shear mode. And then you will find overall deformation of the structure can be much less than the deflection that is given by a structure behaving in cantilever. So you can see, by combining the strength of the frame and the wall, we can go for something like 70 to 80 story buildings. And then frame tube structures. This is one of the very important innovations by an Indian engineer called Foots Khan. He actually he was born in the area that we call Bangladesh today, but he was born in 1920s. Those days, it was all one India. There was no Pakistan, no Bangladesh. It was only one country, and it was India. He was born in India, but actually he is from the area what we call Bengal, the Bangladesh, where the people speak Bengali, which is a language very similar to the Sinhala that we speak here. And their habits are also very similar. They don't eat, their food habits are very different. They don't eat the normal food, the Indian food. They eat rice and curry. And they talk like us. And they are all very nice, kind-hearted people. So this engineer was born there. Then he went to America as a Fulbright scholar. Then he moved on to tall building sector. Then he did a very important innovation. His innovation is based on a biological structure, that is the bamboo. He thought bamboo is very strong, but it has no core. So if we have a building which is very strong on the outer skin, then we can have a structure that is behaving like a bamboo, very strong. Bamboos are very strong, but there's no core. So he looked at it, he developed this concept, tubular structures, frame tube structures. And then people went further and they developed 2 tubes rather than 1 tube. Then they went even further, they started combining 4 tubes or 9 tubes together. And if you look at Sears Tower, it's a 9 tube structure. It has 9 tubes. And Sears Tower was one of the tallest buildings and it dominated the skyline for a long period of time. And they said Sears Tower has an office at the highest level. Sears Tower is having an office in the 103rd floor. And they said Sears Tower has an office at the highest level because Petronas, all the other buildings, they are talking with all the other gadgets, but not a habitable floor. But Sears Tower had a big problem. Similarly, World Trade Center also had a big problem. What is that big problem? If you have a restaurant at the top of Sears Tower, and if you have a wine glass, you'll see the wine is shaking. What is the reason? Building is moving, and it's moving too much. And because it's moving too much, you can feel the acceleration. But nevertheless, they use that building. And then you'll ask again, why they constructed such a tall building? They wanted 2 buildings. Later they found, because this Khan is involved, he said, let's combine 9 bamboo and create a super strong bamboo. Same way they combined 9 tubes and created a very tall, elegant structure, which you needed very small quantity of steel, very efficient structure, very economical structure. So they went for that. Bundle tubes, brace tube structures. And in addition to tube, you get bracings, outrigger brace structures. That is, combined in the outer skin and the inner columns by using large internal beams. And then you will make it even more stronger by running a beam, deep beam on the outer periphery of the structure. Then you call it outrigger brace structures. You get outriggers and then belt trusses. Then you get some structures where when the architects say, I don't want any columns on the outer periphery, there is no option, no other option. Only option is hang the structure from top. Then these days, you can see they are getting very odd-shaped structures. In the Middle East, they don't know what to do with their money. So they are structural engineers, architects and structural engineers to come up with very unusual structures. To me, although they look nice, they are challenging, but that should not be our target. We can have few of them, but all our future structures should not be like that. They should have very simple structure, very efficient structural forms, and then a minimum quantity of material. One good example is Altea, the currently tallest building having 68 floors in Sri Lanka. And we should be proud that we are having such very nice buildings in our small country. And then in Altea, we have used a very efficient structural form. We call it a space structure, and that is called diagonal grid. And diagonal grid, the advantage is you can have a normal structure like Altea. On the other hand, it's also possible to have a very complicated structure. Again, you will use the same concept, that is 3-dimensional structures. So 3-dimensional structures There are advanced computer programs that can deal with the geometric modeling and so on. But still, you will get a very complicated structure. The construction of those will be very challenging, but people are mastering. And then hybrid structures. And that is part of the structure is like diagram, another part is frame, combine everything, then you end up with a completely new form. So we are going to talk about all these different things. And before I start talking about those, I would like to ask any questions that you have. Engineer Kamala, how about questions?
Yeah,
Are they on the chat box?
Yeah, there are. I will read one by one. In case of continuous slab design, is it required the moment distribution at interior support without using maximum sagging moment derived from coefficients?
No, actually, you don't do anything very special moment redistribution. If the moments do not match, it is recommended to adjust the moments. It's not a moment distribution, because if you have two slabs, adjacent slabs, which are having different spans, then you are not going to get the same support moment. But you can't have two different support moments because that is going to rotate the beam. So what you do is you will adjust the support moment sufficiently so that the rotation of the beam can be made almost here. So that is the answer. So basically, don't do any special moment redistribution because already all those different aspects are taken into account when E-line theory was used to derive those coefficients given in various handbooks and codes. So basically, design manuals, you can find different coefficients, but they are all similar. But if the sizes of the steps are different, then you will end up with all these additional problems. So that's why in tall buildings, generally we try not to do things that we'll do in a two-story house. The two-story house, you can make it as complicated as possible. Still, you can decide. But if the architect goes in the same kind of mindset and start designing a tall building, then we are asking for trouble, because in a tall building, what belongs to the architect is the facade, not the structure. Structure belongs to structural engineer, because only the structural engineer can come up with economical solutions, and then he will say, okay, now this is my structural form. You can do anything you like with the facade. Whatever you do, I'll accommodate. And also feel free to do whatever you like for the facade. But don't touch the structure, because structure, I have got it right. And I don't want anybody changing the structure, because it is my responsibility to make the structure as economical as possible. Only the structural engineer can do that. But you're free to do whatever you want with the facade, because people see only the facade, not the structure. So that's the way you look at it. And any structure that is initiated by the structural engineer, you'll find the structure is very efficient. On the other hand, you join the team of architects at a later stage at the structural engineer. Now, most of the building has already been planned. You do not have much control, because everybody else is already into the project. So you can't go and say, I don't like this structure, optimize it. You can't do it. So you have to fit a structure to the existing building. That is, it is very difficult and not economical as well. But very often that happens. But the knowledgeable architects, like the person who did the architectural design of Altea, the architect Safdie from USA, born in Israel, and he's a very good architect. He has designed top buildings in Middle East and also Singapore. And in Singapore, there are 3 buildings where all 3 buildings are connected at the roof level at the Marina Bay. And that building was designed by this particular architect. And he has a superb structural engineer called P. And I'm sure you would have heard his lectures. He's a very good structural engineer. He has vast knowledge, one of the top structural engineers in the world. And he works closely with this architect. So it's a very good combination of architect and engineer. So they both talk and come up with good solutions. And one of those is Altea. And then we have this Singapore building, again, a superb structural form. So sometimes if you have an architect who is friendly with you, and if he appreciates that it's important to have the structural input right at the beginning, then you are lucky, you can end up with a superb building. Then what is the next question?
Yeah, what about Professor, there are a few more questions. What about the failure of flat slabs?
The flat slabs can fail in shear, but you can have steel members like eye girders at the column, so that the shear failure of the flat slab can be prevented. So there are proprietary systems, you can use them. Shear failure of a slab is a problem, but it can be avoided with special, not reinforcement based, but steel member based. Slab design diaphragms for lateral load shouldn't consider this factor in reducing slab thickness. Not a problem. The moment you have anything more than 75 millimeters, the diaphragm action will be there. Don't worry. Anything more than 75 millimeters, you cannot deform the slab on its own plane. So diaphragm action will be there. Don't worry. You can reduce the slab thickness as much as possible. But always keep in mind, sound insulation is also important. If you have very thin slab, sound insulation will not be there. People in the lower floor will always complain. They can't concentrate in their office work because all these people are dragging the tables and chairs and making so much noise. So because of that reason, sound insulation of a slab must be given top priority. And you must consider that factor when you are selecting the slab thickness, especially in the optimized forms. So one of the options is you will optimize the slab, save a lot of money, and use little bit of that money to have a ceiling. Use little bit of that money to have a ceiling, good ceiling, sound insulated ceiling, little more money, then your problem can be solved. So you optimize the slab, save a lot of money, use that for ceiling. In slabs acting diaphragms here. That's what is the next question? Is it recommended to over-design the roof slab of high-rise building to improve the overall lateral resistance and reduce overall deflection? It will not. There's no way you can control the deflection of a building by designing the roof slab. It's a wrong concept. Could you please add one more lecture for introducing design in the composite building, which enables simultaneous construction of above ground floors and basements? No, that is a top-down construction. It is not composite building. It is the top-down construction. But there is a system called composite buildings, and the best expert in Sri Lanka is Dr. Pradeep from Open University. Pradeep Tantirike from Open University. He is very good with the deck-based designs, composite designs. So I have invited him to come and do few lectures. He is the expert in Sri Lanka for this type of construction. So Mr. Senaka also knows. Dr. Pradeep uses it a lot. So I have invited Dr. Pradeep to do a lecture. But the most important thing is when you are buying the steel decking material, it's very important you buy a proprietary product, and some best products would be something like the Blue Scope, which is a very old, well-known name. Don't go with cheap products when you are using deck material. Deck material has a thickness of 0.7 millimeter. When you are using deck material, as reinforcement, you must use a properly manufactured deck material with sufficient corrosion control. Otherwise, you will find huge amount of problems. And if you go to our ISL own building, steel building is already showing signs of corrosion, which is not a good indicator. Always you have to keep in mind, any deck material that you use out of steel must be out of the best steel with best protected steel, so that it's not going to corrode. Because corrosion of a slab in a tall building is a disaster. So you have to be very careful when you are using all the different systems. Then there is the next one. Could you please add?
It's a request.
These are requested. So Dr. Pradeep from Open University will come. He's a graduate from Luna University, and he is supervisor for undergraduate workers, Dr. Sujiva Levan Gamage. He has done his PhD in Rome, and he's a real expert on dynamics. So you can contact either Dr. Sujiva Levan Gamage or his student at Runa, Dr. Pradeep, for any dynamic related matter, or you can also contact Dr. Kushan Vijayasundara for any dynamic related matter. So there are 3 experts in Sri Lanka for dynamics. Dr. Sujiva Levan Gamage from, he's not doctor now, he's Professor Sujiva Levan Gamage from Morato University, or Dr. Kushan Vijayasundara from Perajan University, or Dr. Pradeep Tantirike from Open University. So there are three people. We are lucky. We are having a lot of people who can do all this. And then, sir, can you explain about wind tunnel testing in upcoming lectures? Yes, I will get one of the key experts. He's ranked, he's within the top 10 experts on wind engineering. He's Dr. Asiri Veerasurya. He's from Hong Kong University, and we'll get him to do a lecture. And then we'll also get Professor Sujiva Levan Gamage to do a lecture on wind for Sri Lanka, because he has developed the wind map for Sri Lanka, which has been adopted. And we are again now planning to do slight modifications for this map, so that it will look like the map that we have used with CP3 Chapter 5 Part, but not the same. We'll have slightly similar features, because the map that Dr. Sujiva developed with one of the lecturers at ITUM University of Morato, he did his MPhil with Dr. Sujiva or Professor Sujiva, and that map is based on the available data. So in the areas when data is not available, then the results may be for a lower wind speed. So once you develop the map, you need some modifications. And now we are in the process of doing those modifications. It will appear as a research paper on Engineer Journal, and that will be the final wind map for Sri Lanka. It will come up shortly. So in the meantime, you can make use of the wind map that has already been adopted for Eurocode. And the moment the new map becomes available, we'll get Sri Lanka Standards Institute to add the latest wind map to the national annexure for wind load. So I think I have answered most of the, okay, if building is supported on end-bearing piles to peaty soils upper layers, how do we transfer the lateral loads to the ground? Yes, you have to consider it like a table. You have one leg not stable, but a table is very stable. So you create slabs and have a thick beam-based correction for all the pile caps. If the pile cap is 1.5 meter deep, you will have a connecting beam of another 1.5 meter. The moment you have a connecting beam of 1.5 meter, then it's like a table. And you know, there are so many piles, maybe 100 piles, connected everywhere. It's like a table. So the moment you socket more, if there's peaty soil, you will socket at least 2.5 to 3 meters into the bedrock. The reason is you want almost perfect anchoring of the pile into the bedrock so that you have fixed end condition at the bottom, and you can make the fixed end condition at the top. The moment you make fixed ends at the bottom and top of the pile, the deformation of the pile will be in double curvature bending, and because of that reason, you will find the deflection of the structure can be controlled very well. And the other important thing is, although you think peat is very weak, most of the peat available in Sri Lanka would not be that weak. We are not talking about Malaysia. Malaysia has very weak peat conditions, and so one area is all peat, but it's ground. And if the peat is not there, there's no country. So there are areas with so weak conditions. But in Sri Lanka, we are luckier. Most of our peat conditions are not as bad as most of the other countries. So because of that reason, most of our peat layers can be limited to about 6 meters. Very few places like Orugodawatta, you get 10 to 12 meters of peat. So basically, you don't have to worry too much. If you have peat soils, make sure you anchor it at the bottom, anchor it at the top with a beam system. The moment you do that, rotations will become minimum. The piles will bend in double curvature bending. Because of that reason, you need full length reinforcement. Whereas in Altea, we use one length reinforcement. That is only one length of 12 meters. Because the structure engineer is so confident, there's no need to use any reinforcement below 12 meters because nothing is going to move this building. So don't waste reinforcement just by putting it down to the bottom of it. So basically, we have answered most of the questions. So we look at what is the time now?
Now it's 8:37. Professor, there's one direct question to me. Shall I read it? A small one.
Yeah.
When we are planning to use pre-stress slab, how to plan the arrangement of columns?
Generally, I mean, pre-stress slabs, they are very efficient only when the spans are like 8 to 10 meters. They are very efficient because you have to use a minimum thickness of about 180 to 200 millimeters. Generally, you don't go for a thickness less than that. So when you use 200, then when you increase the span to about 8 meters, 9 meters, you need only 220. The advantage of using 220 is the service engineers will ask for drops. If you have 220, you give service engineer, you will be little strict with the service engineer. You might give 125 or 150 drop. Still 70 millimeters is available, and that 70 millimeters is sufficient to have 2 mats of 8 millimeter bars. The moment you do that, you create the washroom drop within the slab, and if you can control the width of that to 1.5 meters, very good, because the maximum space in between two adjacent strands is 1.5 meters. So if you can confine the washroom drop with careful planning to be less than 1.5 meters, the slab does not know there's a drop. The slab does not know that there's a drop. So basically, you will go for not 5 meters or 6 meter spans. You will go for 8 to 10 meter spans, knowing very well the use of 225 to 230 millimeter slab will allow you to have all the washroom drops within the slab. Have I answered the question?
Yeah, Professor.
Yeah. What is the time now?
8:40. We can wind up actually.
Yeah, 8:40.
Yeah.
Yeah. So next day we'll look into each and every structural form. But today I gave some introduction to the tall buildings, especially covering why we should be masters of the game when it comes to Eurocodes. Because Eurocodes allow us to be very adventurous as structural engineers, not like British codes. British codes are very good, they are excellent, but they guide you. And because they guide you a lot, your scopes are restricted. Whereas Eurocode does not guide you, it asks you to use your brain and do something. So you can have enormous varieties of buildings when you go for Eurocodes. But to become familiar with Eurocodes, you must start reading the codes, books like Musti and Manji, McGinley, and I think Alan's book is also coming with 4 Eurocodes. It might come shortly. And then even if it is written for the old code, read the book by Kong and Evans. Kong and Evans, it's for the British code. It's worth reading it because it will tell you a lot of fundamental things. That is very useful. Just read it. Don't spend a lot of time, but just read it. And then there are so many other new books written for the Eurocode. And in Eurocodes, you can again see there are, even in the beam, it gives you B zones, D zones, all kinds of things. And D zone is a place where, B zone is a place where the plane sections remain plane. D zone is a place where the plane sections do not remain plane. All these different variations can occur in a beam. So there are so many advanced stuff included in the Eurocodes. And make sure that you have read about all those things, and as a result, you feel very confident that you know a lot about Eurocodes, and using Eurocode is not a challenge for you. And by using Eurocodes, you are willing to take huge challenges by stretching the materials to the limit and structural capabilities to the limit. So, what is the question?
That's all.
Kamala?
That's all the question. But there's a small request. Can you explain wind tunnel test in upcoming lectures? It's a request. So, with that,
wind tunnel, I'll get Dr. Asiri Veerasuriya. He's a real master of the game. And in addition to that, the good news is we are trying our best to get a large wind tunnel in Sri Lanka funded by an ADB funded project having a value of 30,000 million rupees, which is actually under Professor Sujiv Levan he's the director of the project. And we have submitted a proposal for a large wind tunnel to be installed at Sri Jawaharlal University, so that all of you will be able to see how the wind tunnels work if the project goes through. And it will be something like 80 to 100 million rupee investment. And if it all happens, we'll be very lucky. And similarly, we are also working on a shake table. And that shake table, our Vice Chancellor has agreed to fund it. If we are going to manufacture the shake table in Sri Lanka without importing it, and we said we are going to do it. So now we have started that. So with those 2 pieces of equipment in one of the universities in Sri Lanka, you will be able to do a lot of experiments, and it will be very useful for many engineers. So basically, wind tunnel will not be. We are going for wind tunnels in Sri Lanka as well, and the instrumentation cost alone is about 50 million rupees. That is just the instrumentation, not the wind tunnel. But so overall, it can be anything in the range of 80 to 100 million. So have I answered the question?
Yeah, we can wind up. So shall I call Engineer Srimavitan to deliver your the
Yeah,
vote of
and also I have a note on this. I can share that note with you. So basically, if shall I send it to you, Engineer Kamala, so that you can make some arrangements with Engineer Manjula to get the email addresses and form email groups, so that whenever we want to
we
email
will,
some edition, yeah.
Yeah, we will ask ISL to dispatch like this webinar. We can ask them to put the email to everyone.
Yes.
That can be done.
So after the lecture, I'll send it to you with PowerPoint. Also, I'll give a copy of the PowerPoint presentation. Then you can share it with all. And if you can make it some kind of downloadable material with links, then all the participants will be able to. You don't have to send the presentation; you will send only the link, and they can download.
Yes.
And I think it's ideal if you can form an email group. So that we'll be able to share a lot of materials in future as well. Okay, then I'll stop here.
Yeah, thank you.
Yeah. Good evening, everyone. So as usual, I'm taking this opportunity to deliver the vote of thanks. First of all, as usual, the Professor Jayasinghe, in many years, I'm known to him, and also so this lecture was very useful, very informative, and the structural forms you explain a lot, and a lot of factors, lot of things you have explained is very useful actually. And also there were many things that I also couldn't remember, that I pick many points. So it's very the privilege to thank at this forum. And so you are sharing your knowledge with us. Thank you very much. And so I hope that we'll follow more lectures in the future. And also thank you for the ISL hosting this event, and also the IT team, and also the organizing team of this lecture series. And finally, all the participants who participated in this lecture. And without you, actually, we can't make this lecture series success. Thank you all, and have a good evening, good night. Thank you. So we'll see in another lecture next week. Thank you very much.
Thank you.